Hello everyone. My name is Tushar. I work as a technical lead at Infocusp Innovation, where I mainly work on a lot of computer vision problems, a lot of NLP problems, and in general any MLDS problems. Today I will be talking about introduction to a TensorRT optimization for computer vision models. So what we'll be covering today is what is TensorRT, what sort of optimization does TensorRT provide on your model, how would you convert your model to a TensorRT, how do you profile the model for a throughput and latency using specifically the Insight Deep Learning Designer tool, and finally, if you have some time, I'll go over how you can run inference once you have a converted model. Okay, so what is TensorRT? So TensorRT is basically an SDK designed specifically for high performance deep learning inference. Uh, it takes your pre-trained neural network model and it optimizes the model execution graph for deployment. It basically tries to maximize the throughput and minimize the latency on your NVIDIA GPU, and it does this through various optimization tactics such as precision calibration, layer fusion, kernel auto tuning, and a host of other optimization that we'll be covering today. So, what do you need in order to convert the model to a TensorRT format? So, first of all, you have to have a trained model. So, this is a post-training operation. So, if you are training, you are still in training, you can't use TensorRT. You have to have a trained model. So, it doesn't matter which framework you are using to train model. Second thing you need is an NVIDIA GPU because TensorRT only works with NVIDIA GPU. And the thing you have to keep in mind is you have to have access to a GPU where you're going to be deploying your model because the optimization TensorRT does is very tied to the GPU that you are using. And the third one is an optional thing. You need some sample images if you want to do a specific type of optimization that we'll be covering later. So, for example, if you want to do like int8 calibration, you will need some sample images in order to do that. Okay, so let's go over some major tactics just TensorRT uses in order to optimize your model for inference. And the first one is layer fusion. So to understand how layer fusion works, so let's take an example of a typical convolution neural network. So the image on the left you would see is how a typical convolution neural network looks like. So you have uh, inputs, you have all your operations represented as a node, and each of these node you can think of it as a CUDA kernel. So when you run an inference on this graph, what you have to do is first load your image into a GPU memory. From that, your convolution kernel will read the data and load it into a register, perform its computation, and then saves the data back to a GPU memory. Then the next kernel, in this case is a BIOS, just again reads the data from the GPU memory, loads it into a register, performs the execution, and writes it back to the GPU memory. So as you can see, there is a lot of back and forth happening between reading the data from the GPU memory, loading into a register, and again saving it back to a GPU. So this takes a lot of time. So in order to optimize it, what you can do is instead of that, you can try to find a sort of operations that are happening very frequently together. And instead of running them individually, you can sort of fuse them into a single kernel. So for example, you would often see this convolution operation and ReLU very frequently come together. So instead of two separate kernel, you just write a third one that does both of this operation as a single kernel. And so that way you can just avoid uh, writing and reading memory from the GPU. Some other example of kernels that you can fuse is like convolution and batch normalization operation, and again convolution. So these can fuse a lot of point operation you can fuse. So it's not possible to fuse all of the operation. So most of the point-wise operation you can fuse easily, but for example, you can't fuse to convolution operation because uh, in order to perform a second convolution, you have to have access to a larger area rather than just a point-wise area. So this is an example of a vertical fusion. TensorRT also does something called horizontal fusion. So if you have if you look at models like Inception Net, so it has a lot of branching. And so each of these branch again has its own kernel. And if the size of the kernel is same, you actually don't need three separate kernel. You can again fuse them into a single one. So that is called a horizontal fusing. Uh, so the next set of optimization that TensorRT does is called it's quantization basically. Uh, so what we do here is, so instead of representing your model weights and activations into a full precision, which is FP32, you basically represent them in a lower precision, like FP16 or int8, and that allows you to reduce a lot of computation. The distinction here I would like to make is only this intermediate calculation are happening in lower precision, but the final output needs to be in full precision FP32. So if you think about, like, let's say your data, your activation values, you quantized them into int8, your weights also you quantized into int8. But when you perform the convolution operation, when you aggregate the values, the final value may not fit in int8. So you need a full precision in order to store the final output. And in fact, if you have some GPU that have a tensor core, these tensor cores are specifically designed to be very efficient at doing this multiply accumulation operation, where your multiplication happens at a lower precision and the accumulation is ultimately happening at a higher precision. So if you are doing like FP16 quantization, it generally works really well. Like you don't have to do additional setup in most of the cases. And you'll get a pretty much very same accuracy as full precision. There are some layers that may give you, they are sensitive to FP16 quantization as well, like specifically a normalization layer, but you can sort of choose where to apply quantization easily using TensorRT. Uh, the int quantization is a bit different case. So because uh, if you think about it, you have a very small range, like your value in int8 is basically only between negative 127 to positive 127, sorry. But luckily, if you look at the distribution of your activation value, most of the time they lie in very narrow range, like -6 to 6 only. So what you can do is you can basically do a min-max scaling over this narrow range. And that way you can make it work. And TensorRT also goes a step beyond. So instead of doing this min-max scaling, what it does is it tries to estimate the distribution of your activation values for each layer, and then sort of try to reduce the KL divergence between your FP32 distribution and your int8 distribution. And if it's not able to match, sometimes if it's not able to get the error very down, it may not use int8. So it can then fall back to FP16 or FP30, 32 precision. So how do you get this activation distribution? So in order to get that, you have to have some sample data. So, and you have to ensure that this sample data is good enough, a good representation of what you would get while doing when you deploy this model. So once you have that data, you can just pass it to TensorRT. TensorRT will run inference using this data, and then it just stores the activation value at each layer and basically measure what would be the scale required to do int8 calibration. Okay. There are other set of optimization that TensorRT does. So namely, there is something called kernel auto tuning, which basically means, like, for each type of kernel that we have, like think about convolution. There are many ways you can implement this convolution operation, and not all of these are suitable for GPU. So I mean, for a given GPU, you don't know which one is the best implementation. So TensorRT basically goes through all implementation of a convolution and tries to find the best implementation for the GPU that you have. There are other minor optimization called constant folding. Like if you have some operation which always takes a constant value as an input, you can sort of pre-compute them. If you have branches in your graph which are not being used by any other network, part of the network, you can just remove them. There are things called dynamic tensor memory allocation, which basically means like instead of pre-allocating memory for all the intermediate tensor, uh, what you can do is you can share memory between tensors that you will not be using at the same time. And the final one is something called dynamic shape profiles. You get a really good optimization if your input size is static. Uh, but for application, let's say if your application needs your input to be a dynamic shape, and then what you can do is you can provide a set of shapes that are most likely to be received during inference, and TensorRT will try to optimize uh, your engine for the set of shapes that you have given. Okay, so now we know that what what optimization does TensorRT is doing. Let's look at how do you convert your model to TensorRT. So again, there are multiple ways of converting a model to TensorRT. The easiest one is to first convert your model into an ONNX format, which is a common format. And both TensorFlow and PyTorch has a very easy way. PyTorch just have like torch.onnx.export, and it will give you a model into an ONNX model. Once you have an ONNX models, you can use Tensor SDK to convert the model into TensorRT. You can also use Nsight Deep Learning Designer tool that we will be looking today to export and profile your model. Okay, so now I would like to show you how we would convert your model and profile your model in Nsight Deep Learning Designer tool. So this is a tool built by NVIDIA. It does a lot of cool things. We'll go over some of its feature. So this tool takes ONNX model as an input. So I have already loaded a YOLO model. So you can basically just open a file. You have to have an ONNX model. You can just open it and you can go through the model architecture. This allows you to explore and find if there is any error in your ONNX format as well. Sometimes the conversion doesn't happen really well. Some ops are missed and not being converted properly. So this is a great way to go over and ensure that everything was converted correctly in ONNX format. So as you can see here, our input is a 640 RGB image, and this is our full model. And at the end, you can verify what the output would be. So since it's the object detection model, it's 300 objects by 6. Your 6 here is your 4 box coordinate. You have a class, treated class, and these core values. Here you can also edit this graph. So everything here you see is editable. So you have something specific post-processing or pre-processing operation that you are doing. You can actually add, let's say if you want to add NMS, you can just find non-merge separation node. And this is a very easy way to just connect your output and input. It's not actually correct, but I'm just showing you how you can do that. So yeah, you can edit it very easily. Once you have your ONNX model, once you are satisfied with the model, let's go over how would you profile the model. So you have to run this tool on the machine where you have a GPU access. So I am running it on a GCP virtual machine. So I have a T4 NVIDIA T4 GPU connected to this machine. So in order to profile your model, you go to this profile model tab. Now there are multiple things you can tune. There are a lot of tactics that you can explore. So let's go over them one by one. So first set of tactics you see are mostly related to precisions and calibration. So as we have discussed, you can select at what precision you want to optimize the model. So you have option like FP16, you have BF16, which is brain float 16. So if your GPU supports BF16 format, this would be a really good speed up as well. T4 doesn't support BF16, but you have a model. If you have a modern GPU like A100, or if you have Google Tensor chips, B416 would be a really good choice. You have in-date optimization. So this is mainly about precision. Then there are other set of optimization. So there is a level on how much you want TensorRT to work on optimizing the model. So if you set it to fry, it will spend a lot of time. It will try a lot of different tactics and will find a best set of parameters that will work for the model. But it will take a lot of time as well. Another thing is the stream. I will cover the stream later. Other thing you can do is optimize for a specific batch size. So uh, if you want to optimize for latency, generally you set the batch size to 1. But if you want to optimize for throughput, if you want to maximize utilization of CPU, you can try multiple different batch size and you try to find which one works the best. If you want to do int8 uh, quantization, then you have to provide a sample data, as I said, so that you can estimate the scale factor for each of the layer, and you provide that cache file here. Next is, yeah, this is some basic settings, like how many times you want to run the inference to estimate the latency. So let's not do any tactics. Let's just set FP32 and it will just try to optimize the overall CUDA graph. And so you can launch the optimization from here. Uh, if you have not installed TensorRT, it will first install it and then start the optimization. Since I already have that, it just launched into optimization right away. So this could take a while depending on how many tactics you are exploring. Since you are not doing anything, this would be much faster. Uh, so let's just give it a couple of seconds. Okay, so it's completed the profiling. It will now, uh, so it has built the engine, now it will be profiling. So once this process completes, it can take some time, but once this process completes, what will give you is sort of a profiling report that looks like this. Uh, so there is a lot of information here. So let's go through them uh, one at a time. So the first thing is the overall summary. This gives you your median network inference. So this model has a 48 millisecond latency uh, at FP32 precision. It needs about close to like 75 MB memory, so not that much. So this gives you just a high level overview of what is your latency. Next set of things is this throughput related. So this is a very interesting graph. So there is a lot of information here. Um, so this stream shows you two type of nodes. So there is a blue node and a yellow node. So yellow node are the kernels and blue are the data transfer. So if you can see, it start with copying your data from host to device. So this operation represents copying your image from CPU to GPU. Then it launches the execution. So now it runs the convolution operation on the data, and then it goes back and forth between a data operation and the compute operation. Next, it gives you a set of throughputs. So VRAM is basically throughput of your GPU RAM. So as you can see, we are not using a lot of memory because model footprint is not that much. PCIe is the throughput between your the host and device. So we are only using that when you are copying the model. Sorry, we are copying the inputs and then we are not using any of it. So as you can see, it's just empty. If you can see, this is a tensor core utilization. As you can see, it's completely blank. It's not being used because we are not using tensor cores. We have not converted. So we are not using FP16 precision. So that's why it's completely blank. And then you have your overall GPU utilizations, SMFT, like how many cores, how much your GPU is being utilized. And basically we want to maximize this utilization. And In case of Vivolo, the architecture is well designed to maximize utilization. So as you can see, it's really utilization is really great. Uh, Next set of things that it provides is it will give you a list of all of the layers, and it will give you inference time per layer. So you can sort of sort your layer based on the inference time. So it will give you like this convolution operation was taking the longest. And if you click on it, it will lead you to a graph, your execution graph, and it will show you where that the node is. This will be a really good tool when you are designing a new architecture. So you can investigate what part of your network is leading to a high inference. Uh, Okay. Next set of details gives you is a precision per layer. Uh, okay, let me zoom out. Okay, yeah. So next set of is what type of how much latency you are getting for different types of layers. So as you can see, there are two type of convolution. So this is just a different implementation of a convolution. So there is you have a cast convolution operation and cast gem convolution operation. Both of them are basically a fused convolution operation. But based on the size of the kernel, sometimes one implementation works better than the another. So TensorRT basically decided that for some part of your network, cast convolution works out to be best, and this some other part, the gem one worked out to be best. So this will give you an idea of how much latency is being uh, per layer. And then you have a distribution of your precision. So since we are not doing any reduced precision, everything is happening in FP32. Okay, so this is all the information that you will get once you have this profiling completed. So now let's look at some of the tactics you can apply. So let's go back to the ONNX model. Let's go back to profiling and let's enable FP16 tactics. And let's just do that and just launch. Let's see how much improvement we get in a latency. So now that we are adding some text, this will take a bit longer. So I will skip that. I already have a report. You can directly go to that. So once it will convert, once it completes, this is what you will get. So as you can see, in FP32, we are getting close to 50 millisecond of latency. And just by doing FP16, the latency came down to 14 milliseconds. It's like 3x, 3 times drop in the latency. You'll also see that your memory requirement also reduced a lot. So from close to 75 MB to reduced to 36 MB. And if you look at the throughput, now you would see that there is an activity in tensor core utilization as well. So now we are using tensor cores. If you look at the distribution down here, now you see that you have a cast convolution operation is now fully using FP16 instead of FP32. Let's enable some more tactics. So let's again go back to a profiling. Okay, let's see what else you can enable. So if you enable a tensor intate tactics, let's enable all three and just launch. Sorry, I'm running it on. Okay, this is still running on GP. But so once you enable intate quantization, this is what you will get. So compared to FP16, so from 15 millisecond, it dropped to 10 milliseconds. So not a lot of drop, but some drop. If you see the precision per layer, you notice that not everything got converted to intate. So within cast convolution, some layer were still is using FP16 and some layer are using intate. So this is because of TensorRT. So it will try to reduce the scale divergence between your FP32 activation distribution. And if the error bounds are really high, it might not convert into int 8. It will just use FP16 in that case. Uh, yeah, that was int 8. So the int 8 typically gives you a really good inference, but there is also a catch. So your accuracy will also drop a bit. FP16 generally doesn't drop that much. Okay. Let's go back to again profiling. Let's see some more tactics here. Okay, so we can look at the stream tactic. So what stream does is, so let's say if you have a model like, let's say Inception Net, might have that loaded here. So let's think of a model like InceptionNet. You have a lot of branches, and these branches are not dependent on each other. So you can actually run them parallelly instead of waiting to complete one branch and then launching another branch. So these streams allows you to run things parallelly. So if you enable, if you set like 3 streams, so it will launch 3 parallel CUDA streams, and it will overlap the data transfer and the execution part, and we'll try to optimize that way. So for in case of YOLO, it didn't really help. But if you look at a model like, so this is a profiling for RTD-TR model. And in this case, 3 streams was working the best. As you can see, it overlaps data transfer sometimes with the kernel execution, so that way it can process the uh, both of these branches parallelly. It's not guaranteed that this will improve a lot of inference time, but it will give some jump. Okay, I think I've covered most of the things. Finally, once you are satisfied with your settings, to get a final engine file, you basically, instead of profiling, you run your export TensorRT engine, and this will give you a TRT file that you can use uh, to deploy the model. And I can quickly show how that would look like. So once you have this TRT file, the deployment scripts is very straightforward. So you can just load the TRT directly using the TensorRT runtime. Next, you have to do some setup. So you have to allocate memory for your inputs and outputs on both your host and your device. So from the context, you will get exactly what's the shape of name and shape of the input and output is going to be. So you basically pre-allocate memory on your host device for both input and output, and on your CUDA, on your GPU as well. Once you have that, you tell your context where you should look for the input and where you should save the output. Uh, then you set up a stream. Uh, Once you have your data, you have to copy that data into, first of all, host memory, and then copy it into, first of all, copy it into a device memory, and then using PyCUDA, you can copy it into your host memory, and then you can execute uh, your context. Once your inference is completed, you can just look at directly your output uh, memory location, and that will give you output. So you have to copy back from device to host, and that will give you your output. Yeah, so this was an overview of how to convert the model to TensorRT and how to profile the model using the NVIDIA Designer tool.